Today we have two speakers, Jessica Terna and Mika Rubinoff. First speaker, Jessica, comes to us from Ohio State University. She's been in the field for numerous years looking at various neurological disorders, specifically schizophrenia. She has a lot of experience with multi-institute organizations such as the Trend Center based here in Georgia State, which focuses on reproducible translational research, and the Enigma project based out at USC with Paul Thompson, focusing on reproducibility as well as code sharing and standardized calls across MRI. She has years of experience dealing with multiple groups, trying to cohesively bring people together. And I'd like to welcome her and see what info she has for us.
Well, thank you so much for that. Let me share my screen here and we will go ahead and get started. Okay, let's see if we can do this again. We did it once. Can we do it again? All right, here we are and go. Right, we good? Okay. All right. Well, thanks so much for inviting me to this. I wanted to speak a little bit about why we might code, why we might share our code, and what we might want to consider when we're thinking about sharing our code. So one of the things I wanted to go back to is what we ask about when we're doing our scientific research, when we're trying to determine the next question. It depends in part in how we think about our science, and how we think about our scientific questions depends on what we know. What do we think are the current models of whatever it is we're studying? Where do we think the gaps are? How do we formulate our questions? But it also depends in many ways on the skills that we have and the resources that we have at our disposal. I am not going to propose an epidemiological study because I don't have those skills, right? And I don't have those resources. I tend to think in terms of what is going on in the brain because that is the skills and the resources that I have. When we share code, we basically share the skills that we have. We help build the skills that other people have, and we share the resources that we have to build the resources that the scientific community has. So this actually improves scientific research when we share code, believe it or not. So in neuroimaging research, obviously, as many of you know, computation plays a really significant role, both in the skills that you have and the resources that you have. The computing systems, the networks that connect them, the data and the analysis, the algorithms and the programming, all of these really play a role in our ability to do scientific research within the domains of neuroimaging techniques. And though that leads to how do we think about our computational problems, how do we actually abstract the data into something that ties into the concepts that we are trying to research, etc. This is actually from California's K through 12 computer science standards, these images, and they're not wrong. This is how we should be thinking about what we're doing and how it plays a role in our neuroimaging research. And that leads to how do we share the resources and the skills that we have with each other. So why might we share our code? For those of you who are actually running a lab or considering running a lab, sharing code within the lab is a very important step to facilitating how your lab is going to actually do work in neuroimaging, leading to repeatable analyses within our team so that you can, person one and person two, even within the same lab, can take the same approach to neuroimaging. It's part of how you train your trainees, is in how are they going to do the analyses they're going to do that often works from a common code base. We also share code to allow replication of analyses and to facilitate reproducibility. I'm sure all of you are familiar with the idea of the reproducibility crisis in every area of biomedical research and psychological research. And this is something I said to my grad students at Georgia State, is you should expect that people are going to come to you when you have published a paper and say, give me the data, give me the code. Because there are more and more examples of people's careers going down in flames because it's found that they've published work that didn't actually happen. Right? And that when somebody comes to them saying, give me the data, give me the code, they can't produce it. And there have been numerous scandals in the past years taking down, established researchers because they were convicted of fraud, in essence. So the ability to show your work when you've published a paper is becoming more and more and more important. And also facilitating reproducibility, right? Not just replicating what you did on the data that you did, but allowing somebody to say, hey, I have new data. Can I reanalyze my data using your code in order to see if there is a similarity here? Because in many cases, when we try to reproduce work we see in the literature in our own data or in our own lab, we know that you don't put all the details in the paper, right? You're going to leave out certain things. You just don't have the space for it. But when I get the code from you, then I can see exactly what you did. Who did you leave out? Why did you leave them out? What exactly did you do? How much did you do this? What order did things happen in? And are there parameters set that I'm not otherwise aware of from reading the paper? And that's just absolutely key to understanding why you do or do not get reproducible results. The last reason I was thinking of as to why we might share code is to really jumpstart the next analysis, right? Once you've actually done the analysis and you have the code, you can now build even more, right? We all have had the experience of reusing modules of code and adding to it. So it really gives you this sort of staircase of progress to be able to share the code and reuse it. So that might be why we might share code with. Who do we share code with? And this is part of what leads to what you think about when you're sharing code is who are you going to be sharing the code with, right? Most immediately, we might share it with our lab members, with people who are collaborating with us on the same project. So we share the code among the people that we're directly working with. Once the code is a little bit more stable, or perhaps as part of your research program, you might share the code with the broader community, the broader research community, and that we're all aware of that software that is being shared with the research community. And it's very important at that point that you be aware that the broader community, much like your lab and other colleagues, is made up of both experts and non-experts, and that will affect how you share the code and what you can expect with sharing the code. And then the most important one, and to me, is sharing the code with our future selves. On the shorter term, perhaps, many of us have had the experience, certainly I have the experience all the time, that I wrote code and then I need it again in the future, right? I've already solved this problem once, let's solve it again. And going back and looking at the code that I wrote, I will often say, who wrote this? Because I have absolutely no memory of what I was thinking at the time that I wrote this. And so being able to share the code meaningfully with your future self is super important. You will think that you put so much blood, sweat, and tears into solving this problem that you will never forget all the details of how you did it. And trust me, 6 months, it's gone. You've had a lot of other things in the way, and you will not remember all the details. So sharing that code with yourself down the road and planning for that is an important aspect of this. Okay, so my background, just so you know where I'm coming from, I'm not a computer scientist. I was raised as a psychologist and mathematician. I was learning to code in order to do data analysis, in order to program experiments, to collect behavioral data, and to do statistics, and then to do neuroimaging. So my background is largely in, right now, structural and functional neuroimaging in cohorts, usually with psychiatric or neurological disorders. I do very little alone. Been there, done that, really don't enjoy it. I tend to work in teams and focus on big data approaches, working with the Enigma schizophrenia approach, which I will say more about later. But I am not coding to build publicly available systems. I'm not coding to change the world in any way. I really am just coding to support my data collection and my analyses for the purposes of getting the projects done and moving on down the road. So that's sort of my viewpoint. And with different backgrounds and different goals, you will get slightly different viewpoints. So I use a lot of different code. MATLAB, R, FSL, shell scripts are my bread and butter. I tend to write a lot of shell scripts just because I'm good at that. I've had to do it so much. Writing more and more R scripts all the time. I used to work in MATLAB. I don't as much anymore. I tend to share all of the above, usually within my lab with my immediate collaborators, such as within the Enigma schizophrenia group, and again, my future self. So let me say a little bit about Enigma. Bear with me if you've heard this before, because I know many of you are familiar with Enigma, but just in case you're not, it was the brainchild of Paul Thompson, who is now at the University of Southern California, back in around 2008, I want to say. He basically was realizing that working with imaging genetics, even as we're all trying to do imaging genetics and we're trying to put together the imaging and the genome-wide association data, and many of us had had experience with collecting 100, 200 people, that no single lab was going to be able to do it. We were going to have to share data. He sent out emails to his incredibly broad network of people doing imaging genetics and said, hey, most of you are focusing on task-based questions. Since you are collecting T1 data, structural data, would you mind, would you be interested in forming a consortium to really look at genetic effects on brain structure, and seeing if we could do it? And amazingly enough, people all over the world said yes, and worked together to develop an imaging genetics protocol based on FreeSurfer and pulling out volumetric issues and looking at genome-wide association data. And very rapidly, this got got feet underneath it. It got legs underneath it. And people, once they got the first paper out looking at genetic effects on the hippocampus and genetic effects on overall brain size, they had pulled enough people together who said, you know what, the data sets that we're working with are schizophrenia samples, because we were looking at genetics of schizophrenia. They're ADHD samples, they're depression samples, they're psychiatric samples. So by 2014, there were already organizing into working groups around these groups of people who had originally contributed to the first genetics paper were sort of self-organizing to say, let's have the schizophrenia people talk to each other and the ADHD people talk to each other and see what we can do. And it has just taken off since then, with more and more working groups saying this is a model of collaboration and data sharing that works for us, that we can actually leverage to get the data sets, even if we're not doing genetics, to get the data sets that we would otherwise not be able to pull together in a single laboratory. So this was probably at the end of 2022, just sort of showing the contributing data sets from around the world and all the different working groups that have been organized. They've basically organized around psychiatric disorders. Those are sort of the first to get going, and neurological disorders, and then every year there are new groups sort of going, can we do this in eating disorders? Can we do this in, cannabinoid use? There's also the algorithmic groups that are really saying, hey, if we get together, we can do better work than we can if we work separately. We'll learn more from interacting with each other. So there's new groups showing up all the time. And since 2010, I've been, or maybe 11, I've been running the schizophrenia group together with Theo Van Erp to really look at what can we do with thousands of data sets collected across multiple multiple scanners and protocols. What can we do? So does Enigma have a central data repository? No, it does not. Some of the working groups have pulled their data together and actually have a centralized repositories. The Enigma schizophrenia group basically was getting started at a time when everybody was very nervous about sharing their data. And we really focused on meta-analytic approaches to say, how do we analyze the data without pulling it all together at one location, because many of the people could not share their data. And that's just gotten worse over the years. Some of the projects have aggregated data sets, so subsets of the data can be shared and they will actually be pulled together and analyzed in a mega analysis, but some of them have not. And so there's really no requirement to share data. Though some of the working groups, I think either depression or OCD, really have some absolutely phenomenal data sharing platforms where they've really worked hard to pull all the data together, but most of us have not. So we use that to really look. I like using Enigma data to look at reproducibility. You can find it once, can you find it again? And if you grab a random schizophrenia sample, if you collect data at your site, how likely are you to find the effect? Because you won't always find it. And how much of this is a reproducibility crisis, and how much of this is just random variability in your sample? So we have focused on meta-analyses, particularly what are called prospective meta-analyses, because we're not doing the standard meta-analysis that you see in the literature where you pull out published effect sizes and da-da-da-da. No, we actually work with the data to say, here, run the same analysis, the same statistical method, send us the results, and we will do the meta-analysis on those results. So we share the results, but not the data. We run exactly the same models with exactly the same covariates on each sample, so you don't have the variability that you get across samples or across the literature. And we focused on free surfer, so everybody has to curate their data, run free surfer the same way, run the analysis scripts that we send, usually our code, and then we can actually get, for example, these kinds of analyses where we can see, there's going to be variability in the effect sizes. And some of these groups would say that there's not a significant effect when they publish the result, if they publish the result. But generally speaking, you see a consensus, particularly in the hippocampal size in schizophrenia. But you can really get a sense for the variability around the world in the effect sizes and what is the consensus result. So the methods are, we usually provide instructions about how to set up the files. We've done a huge amount with FreeSurfer and the fact that they have a standardized output directory structure. We include code to pull the data out and make the spreadsheets. We then provide code that works with those input files and instructions for transferring the output files to a central spot. So we have a lot of code that is being shared, generally speaking. And as you might imagine, when you're dealing with 15 to 18 to 80 different sites around the world, anything that can go wrong will. So people will develop instructions and say, okay, here's, and they just hand out Word documents, and included in the Word documents are shell scripts. And then the assumption is that the user knows to take these in shell script out of Word and how to actually run it in the Linux system, which some sites know very well. Some sites are like, what am I supposed to do with this? The same thing with R. We then include the R scripts, and some people don't necessarily are very good at debugging R, and other people are like, I don't know what to do with this. And error checking is absolutely crucial, as even with all the instructions that we give people and all the help we give them in how to set up their data, there's missing data, they're missing columns. This, just doesn't always work the way you'd expect, and you have to be prepared to handle all of that. So the lessons that we have learned is really to consider who is the intended audience for this code, and what skills are you assuming that they have. Make that explicit to yourself, and then make that explicit to the user so that they know, oh, I can hand this to an RA, it's good, or I really need to have somebody with R expertise or MATLAB expertise or whatever happens. And then how much support are you willing to give the user base for your code? Are you just throwing it out there? Or are you willing to deal with people coming back and asking what seems like really stupid questions to you? I find that it is super useful to assume the user of any code you're trying to share is a new person in your lab who doesn't know how you organize anything, what you expect, what you take for granted about file name conventions, directory structures, etc. Because some people will and some people won't. So it's really important, if you've had experience onboarding new users in your lab and sort of explaining things to them, you need that same level to go with the code, any code that you're sharing. Comments, documentation, and explanation is absolutely critical. I cannot tell you how often I've gotten code from other sites where they're like, here, boom, use this. And there's no explanation about what it does, what it assumes, what the inputs and outputs should be, what the formats are, where they should actually be, what each part of the code is doing, which just makes it unbelievably demanding on the user to do that. So as you would document the code for a friend of yours, you want to document it for the user base, I would say. And sharing with experts and sharing with novices can be very different, right? Which is obvious to experts in R or Python or whatever, may be opaque to novices. You may be, again, making assumptions that they understand something that they don't. On the other hand, novices will read every step and follow it extremely carefully, even if it's clearly wrong, and an expert would know to fix it. So that will lead to problems down the road, because if it's a typo, they will follow it and go, why doesn't this work? And you're like, oh, you weren't supposed to capitalize that, you know? But experts will assume that they know what you're doing, and then they won't know when they get to the end where they deviated because they did what they thought you told them to do, but it's not. So there's going to be errors on both sides. So the goal of your code, of course, is to be fair, findable, accessible, interoperable, reusable, findable. And it is, this plays a role in the lab, even within a lab, and even if you're not sharing it with a broader research community, you want your version control, right? You want to know that grad student 1 and grad student 2 possibly modified this code in ways that are not the same. You want to be able to track that down, and you want to know where it is. You want to make it accessible. Where can people get it from? Interoperability, less of an issue in what I've worked with, but certainly if you're dealing with a pipeline, you want to be very clear about your input and output specifications, and you want to make sure it's well documented, that your paths aren't hard coded to the C drive on your on your Linux machine or your Word your Windows machine, and that you've stated all your assumptions explicitly. It's very difficult to do this after the fact. It's super easy to do it as you're actually writing the code and debugging it yourself. So I highly recommend doing it from the start. Where to share the code? Again, who are you sharing it with? If you're actively developing it and you're limiting it to project members, that has a different set of criteria than if you're actually putting it out there as a long-term archive. I love GitHub. GitHub's great. It's great for active use, and it's great for long-term archive, either public or internal to the project, but novices find it unbelievably difficult to work with. The organization, or the Open Science Foundation, is incredibly friendly for novices, also really good for both active use and long-term archive, but it can be really annoying for professional use coders who are used to GitHub. So it can break the workflow for certain people. We do a lot within Enigma for collaborative online directories. We use Google directories all the time, and website links. That can be incredibly good for active use in a circumscribed group or project. But it is terrible for long-term archive and the larger community. So again, you want to sort of pick your battles based on who you actually think you're sharing with and where you think you're going to go. And then I will wrap that up because I know I'm at the end of my time. So thank you to the broader Enigma and Enigma Schizophrenia group. Theo and Nada were incredibly helpful in writing the original R codes that got everything rolling. I have learned a tremendous amount from working with the BIDS and IDM and RIP-RONIM group, and Lei Wang has been supremely helpful in a lot of the neuroinformatics. And this is, representatives of various Enigma working groups at one of our meetings back in 2019 or so. So thank you, and I think I have to hand it off to Mika and move on.
Thank you so much for that. That was amazing. I'm also glad to see I'm not the only one who looks back at my code and sees how smart previous me was. And speaking of which, using GitHub now, we will move to our second speaker, Mika Rubinov. He's a professor from Vanderbilt. He helped create and maintain the brain connectivity toolbox, as well as the network gradient sampling toolbox for simulated data.
No,
Nope, that's not you.
No.
Oh, okay. I know that's part of your lab, so that's why I.
Oh, yes, that's right. Yes. I see. Yes, it is.
Yes.
Yes.
He's had plenty of experience making code not only available for everyone, but taking in everyone's toolboxes that they send into the brain connectivity toolbox and having to make it still work with other people's code. So please give the floor to Mika, and you have.
Thank you so much. I'm going to make this a little bit less structured, maybe a little bit more interactive. So this will nicely complement the first talk. So, I think here, let me start. Okay, so people see my screen. Okay, so I think there's a basic distinction between coding in science and coding in industry. There are scientific coders, there are professional coders, and they typically have different backgrounds, they have different perspectives, they have different aims. I'm a scientific coder, so I wasn't trained to code professionally, so please take whatever I say with a grain of salt, and ultimately, I encourage you to formulate your own principles for developing general, robust, sustainable code. But I'm going to share at least my experience in doing so. All right, so scientific coders are typically scientists, probably most of you here, who are trying to solve specific questions and often create code that is useful for this specific question, but may not be super general or may not be super robust. Okay, on the other hand, professional software developers often emphasize the importance of generalizability, robustness, user-friendliness, etc. Okay, so on this, based on this distinction, one would clearly say that, okay, it's definitely better to write code as a professional developer rather than a scientist, okay? However, I don't think this is actually the case, because I think you have to think about what your ultimate aim here, and your ultimate aim here is to communicate with your fellow scientists and allow other people to run the code that you have developed. Now, if your code is super general and super optimized and super robust, but it's so difficult and complicated and people don't actually understand how they can use it, then that ultimately creates a problem, because people may not be able to run your perfect code to actually solve scientific problems. Okay, so at the back of your mind, you always have to think about science. We all ultimately try to move science forward, and the code that we build, it should be robust, it should be user-friendly code, but it's ultimately, it's ultimately a tool, right? It's not an end in itself. I'm going to focus specifically on the Brain Connectivity Toolbox as a use case. Okay, so the Brain Connectivity Toolbox, let me just show you for those who haven't seen the Brain Connectivity Toolbox. This is the, let me see. So here's the website of this toolbox. It's a toolbox in MATLAB that is used for computing all kinds of network measures on large networks,
Mika, we're
yes.
not able, if you have the toolbox up, we're not able to see. We can only see your PowerPoint.
Yes. Okay. Oh, no, I was just showing the website, actually. Were you able to see?
We couldn't see. We can only see the slide, the black slide.
Oh, I see. Okay, what about now? Is this better?
Yes.
Okay, perfect. Okay, so this is the Brain Connectivity Toolbox. This is the website, and there's many contributors, and it's we specify the certain idea of what you can use. We have help, and individual functions have help. But the basic idea is that this toolbox is useful for analysis of structural networks, correlation networks in neuroimaging and in other modalities. Okay, this toolbox has been very popular in spite of the fact that it literally violated all principles of good code design, right? It is created in a non-general language. Okay, so if you have a professional software developer, they may not even know what MATLAB is, right? They work in very general languages that are very portable and in principle accessible to many people, right? It has basic documentation. It has informal version control. It's not on GitHub. It has no input validation, and it has no tests. And if you go to the website, it actually says that make sure to test manually that the function is working as intended. Okay, so it's not a very professionally developed toolbox. Despite this, it has been widely adopted in the literature because it clearly was useful for people. And I think that's again a reason why I think we should distinguish between coding for scientists and coding for professional development. Now, I am not suggesting here that you should all write code that is not professional, right? But I just want to emphasize that people do tend to focus on what is useful for them. Okay, so let me just outline, despite the fact that this Brain Connectivity Toolbox was not developed as professional software, why perhaps it was adopted. So it serves a clear need, right? People were interested in this tool, so this was something that they could use in their everyday work. It was simple to install, quote unquote. You just had to copy the scripts literally into your directory. The functions are relatively short. They're well commented. They're generally standalone, and you can go over the functions. And in general, it's relatively easy to read these functions. So I can show you an example. This is an example function from the Brain Connectivity Toolbox. It has a documentation that allows users to gives them some idea of what they should specify, gives an example. And then for people who are interested in looking at the actual code, they can go in and they can read the code, and it's not too difficult. And Another violation, professional software development would say you cannot use single letter variables, right? This is very confusing, but we here follow simply the mathematical derivation of specific network metrics. So in this sense, using single letter variables actually is a little bit more intuitive for us. So just think about this sort of tension that exists at the heart of software development, and think about your target audience, think about the way by which you can move science forward. Okay, so with this in mind, I want to mention now that the Brain Connectivity Toolbox, everyone is happy, but the Brain Connectivity Toolbox now has a caution on its front page, and it says, the caution says the analysis that omit rigorous statistical tests often result in circular redundant explanations. It points to a paper, and the paper essentially says that there is a problem in network neuroscience, and in fairness, in other parts of neuroscience as well, where people do many analysis, test these analysis against fairly weak statistical models, null models, and then report the results as new discoveries. This is a problem when the analysis, the new model they introduce, they're redundant with existing knowledge. This leads to redundant explanations, over-specified models, and in general, a scientific stagnation rather than scientific progress. So I think this is an important problem. It's complementary actually to the problem of reproducibility that Jessica mentioned. So if you think about doing analysis as a type of inference, quite often we don't do inference explicitly, but whenever you test some whenever you do some sort of statistical test, you are doing inference implicitly. You're inferring parameters of some underlying models that may not even be formally specified. Now, the problem of reproducibility, which is a very important problem, refers to the fact that the inference you are doing, the parameters that you infer are highly variable, and therefore the inference of your inference at one type of for one experiment may give you one value of parameter. If you repeat the experiment, they give you another value of parameter. The parameter is not reproducible. Okay, so that's bad. The problem that I have encountered and that I mentioned with regards to Brain Connectivity Toolbox specifically is a different type of problem where you infer redundant parameters with high reproducibility because you test against the same weak null. You show that something is important, that it is reproducibly important, whereas in fact it is redundant. Okay, this is a corresponding problem. It's a complementary problem. In one case, you have a problem of overfitting. In another case, you have a problem of overspecification. Both problems equally lead to bad outcomes for scientific progress. Okay, so for people who are interested, I'm putting this paper out here. So this is a paper where I formalized this problem. This paper says that neglect to test new results against existing knowledge leads to circular analysis and redundant explanations. In fact, key results in system neuroscience affected several thousand papers in network neuroscience, according to my estimates, and serious problem that requires principled solutions. Again, I want to emphasize this is where professional developers deviate from scientific developers. Okay, if a professional developer sees a piece of code that they have put out into the community being used very often, they are very happy in general, irrespectively of what this code is going to do down the track. Okay, now, if you are a scientist, first and foremost, you do want people to use your code, but you ultimately want to make sure that this code is used in a way that does not lead to adverse outcomes for the field. And so what I'm hoping to do now is to give people other tools that would allow them to, perhaps provide them with tools that would allow them to perform analysis a little bit more principled and that avoid the problem of redundant explanations with the Brain Connectivity Toolbox has inadvertently caused. Okay. All right, so I'm going to show you a toolbox that I will release very soon. It's called the Analytical Brain Connectivity Toolbox, or ABCT. Okay, it's a toolbox that uses similar principles and has similar style to Brain Connectivity Toolbox, but the idea here is that the toolbox equates and unifies analysis across several domains and supervised learning, network science, imaging neuroscience, network neuroscience. It's a much shorter toolbox, but each function has equivalents to several analyses that people quite commonly use in the field. And in this way, by providing these tools, and an associated tutorial, this will allow people to produce more unified analysis, produce more integrated explanations of their specific questions of interest. So here I want to mention another aspect that is relatively recent, that has appeared, relatively recent on the horizon, and I think that can help scientific coders such as myself and perhaps many of you here in the audience to incorporate principles of professional development, but at the same time do not distance your audience of fellow scientists. Okay, so okay, maybe I'll just skip this slide. I mentioned this story. So, and this is the summary of the different equivalences that's going to go into the toolbox. So I wanted to mention large language models as a very useful tool that I found that has helped a lot in the development of this toolbox, not necessarily for writing code per se, but for making this code more user-friendly, better documented, and better accessible to others. Okay, so I'm going to show you some examples of the sort of development that I did with this code, and I'm happy to chat later when there's a time for questions, etc. So just going over the previous points that are mentioned from a positive perspective, from a negative perspective, and showing how this sort of toolbox would serve, could fit in. So it serves a need. The need was the need that I previously outlined in the talk. It is simple to install, so it's really in the same way. It's just a bunch of scripts that people can download in their directory. So it's very easy. It's very easy to use. The code is easy to read. And here I have this little sparkles, and I wanted to show essentially how I use LLM. So let me actually show you an example. So this is an example of a function from the ABCT. I deliberately removed the documentation from this function just to illustrate how large language models could be useful in your work. And here, so this is the MATLAB version. And so what you can do, for example, so I'm using this tool called Cursor, but in principle, you can use any large language model. So what you can do is you can literally say, select the code, provide a header and comments to this function, and submit the edits. And it goes ahead and gives you a very nice header. Now, this header may not be very, it may not be comprehensive. It may make mistakes. You can subsequently play with it and edit it, but it does provide very simple and straightforward ways for you to document your code. I found this definitely a very useful tool. Now, in terms of writing the actual code, the outcomes were a little bit of a hit and miss. Sometimes, it really tries to fill in the gaps quite often. And when the function is very straightforward and very, bread and butter, then it does a good job. But quite often the sort of code that you may write is more specialized, and there it often breaks. So I find that large language models are good for things like documentation, commenting, standardizing your code, but not necessarily for writing the actual code itself, at least in my experience. Okay. So easy to read code, short functions. So again, all these things that make scientists, make it easier for scientists to look at what you have done. Standalone functions. This is sometimes not possible. Sometimes your function is just too long, so you have to split it up into multiple. But in general, where you can aim for short functions, aim for standalone functions, aim for something that is relatively easy for other people to understand, and the less, the more bells and whistles you add, the more things can go wrong as well, unless you overcomplicate your code to then fix this bells and whistles. All right, version control. Jessica already mentioned this is super important. I strongly emphasize, it's very important, both for others, for reproducibility, but also for yourself. Quite often, just to revisit what you have done before. For example, if your code may break, where did it break, at what stage. It makes it easy to fix this mistakes. Input validation is something that is also very important. Now, this can become very complicated very fast, depending on how much how much trouble you spend on inputs. I do want to show you some specific MATLAB functionality that's fairly recent, actually, and it's very nice, I think, for testing inputs. So and it provides a relatively compact way to do so. So, for example, so let me show you an example code. So this is like code for mod removal. It has some nice documentation. And then there's this arguments here. So there's this arguments container here in MATLAB, and you specify the arguments, and then here we have X type. And this is the X variable. It just tells you that this variable has to be a matrix, two-dimensional matrix of any size. It should be able to be converted to double precision. It must be non-empty, it must be finite, and it must be real. Okay, so this is a very compact and very user-friendly way to validate your inputs. If you put something like this into your codes and you go and work on another function, the LLM helpfully suggests all these input validations again, so it's very easy to standardize your code. And for example, one more here, type, must be member, so you provide the member, and it must be a string, and it must be one of these types. Okay, so input validation is important. It can get messy sometimes, but modern software allows you to do it relatively easily, and I encourage you to take advantage of this sort of features. All right. Tests. So tests, again, are very helpful. And again, that's somewhat a distinction between software, professional software design, and scientific software design. Scientists may not necessarily often write extensive tests for their codes, and often it may not necessarily be essential for you to do so, especially if the code is quite short and simple. But if you do have a multi-step analysis pipeline and you do expect others to use it, I encourage you to think about how to test this. And again, tools like MATLAB provide you with fairly simple ways to test your scripts. So I can show you, for example, one way in which you can do this. So you can write this. So I have a test option class here, and you can see that there are several properties here. There's the method, the number of clusters, number of batches, objective similarity, start, maximum iteration, replicates, and then it literally just calls this code under the hood. So it's not a very long piece of code, but what it does is it essentially creates a massive hierarchical set of for loops that runs your function perhaps hundreds, maybe even thousands of times, and tests the output and warns you in case there are any problems. Okay, so if your code is becoming quite long, consider tests as an important addition to your code, especially if you want to distribute this to your colleagues. All right, documentation, I already mentioned. Again, something like LLM is very helpful, so make use of modern tools. Language. Okay, so I want to mention language here as well, and it's something that's I think Jessica referred to several times, how codes can be developed and distributed in different languages. In principle, it would be great if everyone used the same language. Unfortunately, in practice, it's not the case, right? I personally work primarily in MATLAB, but I understand that lots of other people use other tools. Python, for example, is very popular as well. And so the question of how you want to reach people who may use a different language to you is an important one, and something that you should think about. And again, I think a place where LLMs can really help. And again, I want to show you a very simple example. So just going back to this code. So I made a Python copy of the original code. It's essentially a MATLAB code, which is a Py extension. And then again, you can ask ChatGPT, you can say translate to Python and submit, and it goes ahead and does a translation of your code. Okay, it translates it to Python in real time. And again, this translation probably has some mistakes. You have to go in and you have to check in the end. but it does provide you with a very simple way to move your code from one language to another and potentially to standardize the use of your code amongst multiple languages. Now, this is not necessarily the most, let's say, pain-free method, especially if your code is under active development. If you continuously change your code in one version of the language, and if you want to continuously synchronize, you have to carefully think about whether you want to keep translating your language with, keep translating your code with large language models. So other options are possible. You can containerize your code, in which case anyone can run it, or you can provide some sort of more general API. But again, this sort of takes you down the path of software development, professional software development, and a little bit away from the path of scientific computing, and just take care to keep scientific questions front and center, and do not forget that's why you're ultimately developing your tools. All right, I will stop here, and I'm happy to chat and take any questions.
Thank you so much. That was phenomenal, and you just opened up the whole world of coding for me with that AI editor. Like, it's definitely something I'm going to integrate into my life now. Let's thank our speakers first, and then also if anyone wants to post questions in the chat, or you're free to unmute yourselves at this time to ask a question to either speaker or both. Yeah, Peter, go ahead.
Yeah, thank you so much to the both of you. So one of something I just have been thinking about a lot is some of my research assistants I supervise, they're still relatively new to coding. And, I think if I were to bombard them with everything that was covered today, they'd probably feel quite overwhelmed quite quickly. I was just wondering in terms of prioritizing what they should maybe focus on the most, whether you had any recommendations. Because, for example, tests, maybe I wouldn't emphasize that as much, but I was wondering if either of you had a recommended kind of starting point that that's the main thing they should focus on.
I deal with that a lot, and with bringing in undergrads from psychology and whatnot. And I think in many cases it depends on what their future goal trajectories are. But many of them have found ChatGPT to be a lifesaver, because I can give them code, I can give them scripts, they can find it online, and then they can run it through ChatGPT and say, what does this do? And the pedagogical approach of ChatGPT is phenomenal in the past year, where it will, it'll go through it line by line and tell you this is what this is doing. And for some of the students that works extremely well. Other students have a little bit of a harder time still, understanding what's really happening. But I think that has really jump-started a lot of the students in terms of being able to work very quickly with R or Python or what have you.
Yes, I agree, and I think they should really focus on the basics, and don't think about things like tests right off the bat. I mean, I think they should just think about how they could write some code that is relatively straightforward, that is well documented, and that does the job that they want to do. I think that would be the first step, and then later they can think about the bells and whistles, or maybe not even think about them at all. As long as if they produce code that is relatively straightforward and that's what you expect them to do, then that's really kind of 90% of the way there.
Okay, great, thank you.
I've also found that having them work in teams and share each other's code very quickly highlights for them where they're falling apart and not making reusable code, or not making things clear, because then they get it from somebody else and go, wait, what? Or they get a really good example from someone else in the lab and go, oh, wait, I should be doing all of this.
Awesome, thank you so much, both.
So I have two questions that I kind of hope you both answer. So in one aspect, first question, like, Jessica specifically, you talked about like the different aspects of sharing your code, whether it's going to be internal, whether you're going to put it on GitHub, or have like even a Google Drive shared with a group. when it comes to going from like sort of a private closed thing of whether it's internal hard drives or a Google Drive to going to GitHub, like what do you think that jump is? Like what level should the code be at before you start hosting it on GitHub and allowing people to start kind of playing with it and sort of, I don't want to say dismantling it, but finding all the horrible things that are still wrong
Right.
with it?
I think there are a number of things to consider in that situation. One is who's in your lab and how compatible are they with this, how skilled are they at this sort of thing? Because there are certainly a lot of labs that start at GitHub, right? And they do it internally in GitHub, and then when they're happy with it, they're like, okay, public download. And other groups that work internally and then put it on GitHub only when they're ready for it to be, when they publish the paper and have to share the data. And there are pros and cons to both approaches. I think the one I have worked with the most is, make it public when you've published it. And I can tell you what the disadvantages of that are, which is that it can take days to really go through your code and say, could somebody who wasn't in our lab actually use this? And find all of the, hidden paths and things like that to really clean things up. But at the same time, it also highlights, it often will identify things that you were not aware of in your code when you do that. So there's something good about sort of having fresh eyes look at it at the end of the project, because certainly the stuff that you build in as you're versioning it and everything else will sometimes still be there if you don't really do that clean sweep. So there's pros and cons to doing it either way.
Yeah, I think in general, you can have an internal lab GitHub repo for all your messy code and all things that are in progress. And in general, I think there's no downside to that, because it really just helps standardize what people are writing and avoids various duplications and code losses, etc. And for public release, well, I don't know. I mean, you just have to be, it's a balance between being confident in what you have written and sort of being eager to share it with the rest of the world. So it's some people are more cautious, some people are more brave. So it's sort of a question of where you lie. So in general, I think you should release the codes with some publication that you produce as a result, but you may choose to release it earlier if you're confident that it is doing the job and people could start to use it. And maybe, as Jessica said, it could actually benefit your code because people could give you feedback and you could actually refine it based on this feedback.
Yeah. And I think it really helps to be from the beginning, as soon as you're starting to write your code, to be saying, I'm not just writing this for myself. How do I write this in such a way that somebody can reuse it, whether it's somebody in my lab or somebody outside of my lab?
Your screen just let me know yes or if I need to.
Thank you. And so I'm gonna ask one more question, but unfortunately, as you both know, I have to leave for a
Oh, right.
spin.
Yes, of course. Sorry.
So you please answer it and I'll say it on the recording if I don't get to stay for the whole thing. But one of the things you talked about, specifically you, Jessica, and your thing was like, don't leave like hard-coded C path in your code. When you're starting off with a newbie, like someone who's just learning to code, they're making their first scripts for the first time, do you think it's okay? I don't know, say okay. Like, would you recommend just letting them do that kind of hard coding to begin with so they can get a flow of the full script and actually get it to working? Or should you really have them focus on doing generalized paths from the start so they don't have to, so they're not like
let them
constantly
do
going
what they
back?
need to do to get to the point where they actually understand one piece of code, right? Just like this testing business. Let's make it work once, then we'll see about generalizing it. Absolutely. That would be my pedagogical approach.
Yeah, exactly. Great. Yeah.
Okay, thank you.
All right, I'll
Thank
let
you guys so
you
much
jump.
Yeah, I
up
gotta
in.
go. Thank you both so much.
Have fun.
Bye, everybody.
We've got one more question in the chat. I don't know if either of you can see the chat. Is anyone actually developing chatbots that can be included in the GitHub repo of your code and run locally as assistance for using the code?
Good Lord, no. I got things to do.
Oh, you mean you develop a chatbot that helps
Tune.
others to figure out your code?
That sounds like
Yeah, that's
Leonardo,
an interesting
you
idea.
can,
I mean, I feel like LLMs are advancing so fast that in principle you could probably give it you can probably, give the directory. And so I can quickly show cursor again. So if you, and yeah, cursor is one example. You don't have to use cursor, but here you can actually chat to the LLM about the code. So if you do Control I, you can ask it various questions about, and you can highlight portions and ask it like, what is this portion of the code do? And then it sort of, I think it sort of acts a little bit like an assistant. It's a generic assistant, but I think it could be a very useful assistant. But yeah, so I don't think it's necessary to develop chatbots specifically coding.
I didn't even know about this tool. This is phenomenal. It might change my life.
Perfect.
Are there any other questions from anyone? There's a couple of links, I think, in the chat that people have given.
Mm-hmm.
Oh, yes. So dependencies in MATLAB, MATLAB actually has one great thing about MATLAB is it has a lot of this sort of professional software design built in, and it actually has you can actually go to a project and it generates a dependency tree between all your functions, sort of a built-in tool within MATLAB. So if you want to explore this, there's a lot of documentation, and it's something that's not too difficult to get into. So it's something that's built in within the actual tool.
Fantastic. Okay, it seems quiet in the chat. I just saw your comment, Jessica. I just want to thank you both. This was so useful for the community. We really appreciate it. Thanks everyone for tuning in today. And we look forward to seeing you at that next how-to workshop. And we'll also put all the links that you guys both raised today into the YouTube video so people can follow directly from there.
Wonderful.
Thanks very much.